Okay, we are now recording. So I'd like to welcome everybody to the Marine Amateur Radio Club in-person meeting. This is the third Thursday, November 20th. And welcome to our Zoom people. There's Pete, and I think it's just Pete for right now. So tonight we are going to talk about something that has always intrigued me. I've always loved making antennas, and it's amazing what you can make out of an antenna. Um, and I was doing a lot of studying today on slot antennas, and I think we're going to have a presentation on that. I've been working, when I say I've been working with, that is to say, I've been watching a lot of Mr. POTUS's YouTube videos, which is where this presentation originally came from. And when I was looking for, DIY antenna building, in particular Yagi's, his name came up on YouTube. And so I started taking a look at all of the antennas that he was making, and he's doing something quite unique. Uh, he's making it simple. So the simple-minded like me can understand what how to do this. So tonight we are going to demystify the Yagi antenna, and in particular, we're going to learn how to build it, build build any of them ourselves. So this is a lot of screenshots I have directly from his presentation. Okay, and I also have his presentation downloaded, but I pulled a lot of the material from his presentation and put it in the Mark format, with the green background and stuff. So, but this is all his stuff, okay? And there's a place where you can download his slides. Incidentally, just so everybody knows, these Mark recordings, these Zoom meetings are being recorded, and they will be on the Mark website. And so there'll be a PDF of this as well as you can watch the video. So without further ado, let's talk about the Yagi antenna. And I think I heard this a long time ago, but it was good to be reminded of it. Yagi wasn't actually the person who invented it. It is Uda who designed the antenna. His name is Shintaro Uda. And the reason why Yagi is even in the picture and why we call this type of antenna a Yagi is because Mr. Yagi was doing all the publication and promotion of the antenna. So that's why we call it a Yagi, but it's really a Yagi-Uda antenna. And so anyway, there's some trivia to okay, just stand by. Can someone talk to Justin on Signal? Send him the link to the Zoom. I mean, we just use the same link every time. So if you could let him know that. Okay, so there's a lot of different Yagi-Uda antennas, and just for the sake of simplicity, I'm just going to call them a Yagi antenna because that's what everybody knows them by, right? So you have like that arrow one where you have a dual band, you pull vertically polarized and horizontally polarized. You have the UHF one, you have multi-band HF. They're all using Yagis. VHF, and even our televisions, our old analog TVs, that's a Yagi that is different kind of Yagi though. So how exactly does a Yagi work? And this is actually quite interesting. If you take a dipole for extra credit, who can tell me what a dipole is? It's the antenna with two elements, right? The center conductor is on one element and the braid is on the other element, right? And so you take a dipole, and let me turn on my laser. So this is the dipole right here. This is called the driver. Okay. And you place another dipole of similar length, a bit longer or a bit shorter, and it will pick up some of the radiation and retransmit the re-radiate is a better way of saying it, the signal that it received from the driver. So here's a director. A director is an element that is slightly smaller than the driver, okay? And now if you place the non-driven element a certain distance from the dipole, the driver, then there'll be a special relationship that is developed between those two. And going in one direction, the re-radiation will be in phase and the other side will be out of phase. Okay, that's why we have gain in one direction and just the opposite in the other one, in the other direction. Okay, so the wave going in the forward direction will add to or supplement, augment the primary wave coming from the driven element. This is, like I say, why we get forward gain. The director element is shorter because being shorter makes a slight advance in the re-radiation of the wave. And it only works on that one direction there. Let's go and why can't let me see if this will work. Okay. So the same thing can be done with the reflector. If you put an element on the other side of the driven element, this time a longer element will produce a slight delay in the wave. The same special relationship will then exist between the driven element and the reflector, and then you get that same thing. You get an in phase a re-radiation, and behind it is out of phase. Okay. As a matter of fact, okay, here's what it looks like when you have a reflector and two directors. We have destructive interference behind the antenna and constructive, augmented in phase going the other direction. And I think it's incredible how that all works. Here's another view of what happens. And this is probably more accurate. And this shows you with the reflector, the driver in the center, and the director, what actually happens. And so as you can see, the forward gain is to your right, and then the destructive stuff is behind you.
Now, this is a transmitting antenna?
Yes. Yep. The same thing happens for receive. Okay. When you have the antenna pointed at a small signal, it also has the same forward gain. It's like it grows a lot bigger ears, right? And I was unable to find a diagram, a GIF that actually shows what the receive does, but I'm sure that there's some physical properties that are slightly different, but regardless, you get the same forward gain receive as you do on the transmit side. Okay, so from about 1926 to 1948, you only could look to get Yagi designs from high-paid radio engineers, right? And back then, it was trial and error for the Yagi design. And today, there's really no a simple way of figuring it out. As a matter of fact, um, a lot of hams are afraid of making a Yagi because if you go online, if you look at your okay, if you look at you Google, how to make a Yagi and cutting the distances and all that type of stuff. There's a lot of different methods of doing it. And so a lot of hams think only high-powered engineers can design the Yagis. And I'm here to tell you that that is not the case. As a matter of fact, in 1948, after World War II came about, the National Bureau of Standards, now called NIST, the National Institute of Science and Technology, created what's called the 688 document, and you can still download it. In this document, it did an extensive study on Yagis to understand the Yagi a lot better. They used the Yagi in World War II, but it was just trial by fire. Okay, they didn't have a formula or anything for figuring this stuff out. So the 6088 has all the equations and graphs that were needed in order to reproduce the performance of the Yagi. Well, I read that document, and unless you're an electrical engineer and into RF, it was a sleeper. But there's another way of doing it. So you can go online and look at a lot of different online calculators. The criteria isn't explained. There's a lot of disagreement with how things are put together. Hams are, of course, confused which to use. And, his presentation, he keeps on downplaying hams. Many hams can't handle the detailed graphs and equations. To me, I thought he was talking down to me a lot. But that's just who he is. Once you hear his YouTube videos, you'll know what I'm talking about. I personally don't believe that, but he has a degree in this and I don't. So I'm not going to challenge him. So he knew that we needed some type of simplification for that. And so guess what? We have the ability to do that. We don't need to be buffaloed by all the high priced analytics that you have to know, the quantum physics, the calculus that you have to know to understand that. Actually, there's only 3 rules that you need to do in order to build a Yagi. And it's these 3 here. And really, the first 2 are the critical ones. All element spacing, every single element spacing, reflector, driver, and director are 0.2 wavelengths apart. Okay. All directors and the reflector is 5% plus or minus length difference than the driver. Okay. And if you have more than one director, then all the directors are equal length and they're equal space. Okay. And that's the thing that blew me away. And so here's an example, and I'm going to pull out this one here. This is a commercial antenna, just like I show on the screen here. And this commercial antenna manufacturer uses the same technique that John does, and that is all the elements are spaced the same, all the drivers are the same, and there's a 5% difference in length between the reflector and the driver, and then the driver to the director. Okay. And so this is one type. Then you have other manufacturers that, if you look at the directors, they're small, they go smaller and smaller, and they're closer together. Okay, as a matter of fact, you'll see a lot of them where the driver is a little closer to the reflector than the directors. There's a lot of different ways of making this stuff. But here's the deal. Well, I'm going to talk about that. So let's create a real live example of what I just talked about. In order to calculate the wavelength, that's very simple, right? We take 300, which is the speed of light in a vacuum, 299,997,000 blah, blah, blah miles per second, right? Divided by the frequency in megahertz. That will yield you, let me turn my laser pointer on, that'll yield the frequency or the wavelength, which is lambda, in meters. Okay. So 300 divided by nu, that's the frequency in megahertz, will yield the wavelength in meters. But we don't live in a metric world. We live in inches and feet. And so to multiply, to get inches out of the meters, you multiply that answer by 39.37. Okay, and that'll give you the wavelength in inches. Okay. So for the frequency of 223.5, which is, and what's that frequency? Anybody know? 223.5. What is 146.52? It's the calling frequency for the 220 band. Okay. Say again? I didn't hear you. Yeah, that's okay. So yeah, this is a 1.25 band, the 220 band simplex, right? And as a matter of fact, this tells you, without the additional calculation, the actual wavelength in meters. So the 223.5 is 1.34 meters long. So, but we call the 1.25 band, meter band, because generally that's easier to remember, I guess. But the 223.500 is actually 1.34 meters. You multiply that by the 39.37, and you get 52 inches, and that is the wavelength in inches. Now, what did we have to do? We had to take the wavelength and multiply it by 0.2. In other words, 2/10 of the wavelength will give us the spacing between each element. Okay, in this case, it's 10.57 inches, or 10 9/16. And as a matter of fact, I actually made this antenna today for the 223.500, and I have to pull that out. But this is the driver, and this goes in the center. This hole isn't big enough, so pretend that this is over here. Okay, but anyway, the distance between this is 10 and 9/16 inches on both of them. Okay, the driver, we haven't talked about the length of them yet, but the first thing is to calculate is the distance between each of the elements. And because this is a simple way of doing it, you don't have to worry about different spacing. It is always 0.2. Yes.
Would you go back a couple of screens that had 3 points?
I'm sorry?
Would you go back a couple of screens that had the 3 points of every Yagi? That one.
So all element spacing is 0.2 wavelengths apart, and 5% plus or minus is the size of the elements. It's really two rules, and if you want more than one director, then it doesn't matter. You just use the same length of the director and the same distance. So, which is actually what I did I made this GMRS antenna, and this is actually completed. And I have 3 directors on here, a reflector and the driver, and following this very same calculation, right?
So the director is what takes the connection. Well,
that's the driver. Well, finish your thought. Maybe.
Okay, so your coax comes up and the center connects to the driver.
The driver.
Okay.
And then the director, they call it director because it's kind of directing.
It aims the signal.
Yeah, but here's the thing. I can get rid of the director and just have a reflector and my driver, and that's still a Yagi. I'm still going to be able to, that still will have forward gain. Not as much as if I were to have the director there. I can also get rid of the reflector and just use the driver and director. And this is also a valid Yagi antenna. Okay. This is also a valid antenna, just a dipole. Okay. But there's no gain, right? Yeah. So now you may be wondering why the different colors, and we're going to get into that. I didn't realize, I thought RF was colorblind, but I guess it's not. It's looking for an orange director. Yes. Yeah. This is a 2-meter fox hunting antenna, homemade. And this just has a driver and a director. Okay. And I use this one when I don't need a lot of gain. Okay. I have other ones that have a reflector on it, right? That has 2 elements. But I was playing around on the distances between the director, right? So this was just a test one that I did, but the concept is the same. You only need a driver and either a director or a reflector in order to make a Yagi. Okay. Yes.
The one I know is, can you use that inch ruler? Do you have to use a metric ruler to make that?
If you have multiplied it by 39.37 to get inches, then this will not work. There's always one. Okay. Does that make sense, Russ?
Yeah.
Okay.
Now, does this use a balun to go into the
yes, ultimately it does. And we'll talk about that. Okay. So we've, all you got to know, I mean, this is the magic number right here, this 52.846. That's the wavelength. Once I have the wavelength, I can figure everything else from that. So I multiply this by 0.2, and that'll give me the spacing. And then the next thing is, turn off my laser pointer. Now I'm going to calculate 5% for the reflector and director. Okay, so I'm just going through the first one, 52.846 inches, times 1.05. That is the reflector I'm calculating, and that gives me that value. And because I'm making a half wave dipole, which I think is something kind of important to understand, when I'm making a dipole, I'm not doing a full wave dipole, right? This is a half wave dipole. So when I'm calculating this, I divide it by 2 to get a half wave, which kind of makes sense, right? A half wave divided by 2, no, a wavelength divided by 2 is a half a wavelength, right? Which is what this is what we make our dipole from. We could also do a quarter wave. It's not as efficient as a half wave, but the antenna is smaller, okay? You can also do 5/8 wave. You know, you can play around with the harmonics of it and do all kinds of stuff, but it is customary and usual just to go ahead and use a half wave for the dipoles. Okay. And so that's why everything is divided by 2, which is half of a wavelength. And so the reflector is 27 3/4 inch, and the directors are 25 1/8 inch. Okay. And again, if I have 1 director or 15 directors, they are all 25 1/8 inch. Okay. So what if you use the complex math and the elaborate graphs and the online calculators? Okay. The only thing that you're going to gain by doing that is about a 5% gain. Now, let me ask you this. Can someone on the other side of your radio hear a 5% gain on a signal? That is...
Yeah, I can't quite hear you. Could you say that 5% louder?
Yeah, exactly. Way to go, Justin. Okay, so you're not going to, 5% is only a tiny fraction of 1 S point, okay, on the radio. You're not going to be able to tell any difference. So, as a matter of fact, what this gentleman did is he took 5 of the very best calculators, and let me get my laser pointer again. And he put this on, he ran it through EZNet. Okay, that's an antenna designer, right? And the composite, he made a composite values of all the 5 best calculators, and this is the result in blue. And as you can tell, using the 3 rules Yagi version, I'm thinking that's pretty good. And of course, this is the azimuth, so this is a bird's eye radiation pattern. And to me, it looks like that you even get a better null from behind you. Okay, it's quieter using the 3 rules Yagi versus the other calculators. And to me, it looks like you get a slight gain on the forward gain. And now that I'm looking at it, I'm thinking that he has these colors reversed. I think it really is, this is the 3 rules versus the composite calculator. But it really doesn't matter because the difference is so minuscule, you're not going to tell the difference. Yes, Russ?
Wouldn't the only real difference between the two be one is slightly more directional than the other? Because you don't have the gain off the back end.
When I look at this, let's say that the red is actually the one that we're figuring out, right? To me, that's telling me that there's more of a null. It's quieter behind me versus hearing things, just slight noise, but I don't think you could tell. I don't think you could hear any difference between those two values. And look at this side. I mean, if I look at this Yagi here, to me, the blue is telling me that I may be able to hear people off at the 8 o'clock position and the 5 o'clock position, versus the red is like, it's quiet. You have to actually do your signaling from the front. I think the main point here is whichever is correct, the human ear is not going to tell. You are not going to know. Okay. So here it is. The steps that you do. You first of all, you start with your dipole. Okay. You mount and tune a driven element on the mast. Okay. That's the first thing you do. You want to make sure that it's resonant on the frequency that you want. And then you add the reflector and directors. And then once you do that, you add the feed point, the matching feed point. And we haven't talked about that yet, but we're going to do that now. As a matter of fact, you fiddle around with the SWR and make sure that the feed point yields you the lowest SWR before you trim the elements. And you trim the elements for frequency. And you do it in that order. You worry about the SWR first, and then you worry about the frequency. Never tune the frequency first, always the SWR. And he spent a couple minutes drilling that into us, saying, do not, make sure you do the SWR first and then the frequency. And it really is that easy. It is very, very simple. Now, let's talk about matching. So something happens, and actually we're going to talk about in the next slide. But there's a lot of different ways to create a match. As a matter of fact, on this antenna here, the commercial antenna, this is a gamma match, right? These are methods for, okay, so let me put it in another way. The moment you add elements in addition to your driven element, okay, either a director or reflector or both, you've changed the properties of your antenna. A dipole gives you about 72 ohms in free space. Okay, what does the radio look for from the antenna? It wants 50 ohms, right? That's why we buy 50 ohm coax. But as soon as you create a dipole, that's not 50 ohms. It's 72 ohms, which is like 1.4 to 1 if you were to compare that to an SWR. Okay, that's not bad. Radios can handle that just fine. Okay. So what they do is they put a match on there, and that brings that down to 50 ohms for the antenna coax connection. Okay, as a matter of fact, there's a better explanation in a couple of in the next slide. But there's different ways of creating that match. There's the gamma match, which is difficult. It's easiest to change because all I got to do is unscrew it and move it until you look at your SWR meter and see what it's doing. But then there's also a J match, what's called a J match. And it's actually a half folded dipole. It's very common where they'll take, actually, I'll do it on this easy. Here's my driven element. They'll take they'll take this element and they'll fold this over on itself like that. That's a folded J-pole match. That's one way of doing it. And then the other way is a hairpin match. And this is what is used on these here. That's the little wire that's connecting, that's shorting the center conductor to the braid. Okay, it's actually shorted. That's changing the impedance of the antenna. Okay, and so the question is often asked, how do I know the distance? How do I know how big to make my hairpin? This is the easiest to do. You just connect it. As a matter of fact, on this one here, on my GMRS antenna, I have a hairpin, and I'm using hose clamps, and I'll pass this around, and it is just hose clamp to both sides of the antenna. Why don't you? Can you?
What's that hairpin made of?
Wire.
Just wire.
Yeah.
It looks like it's dead short.
Exactly.
Yeah.
Yep.
Matter of fact,
I think that's a 10 gauge. I have a 14 gauge that I used for this type. This is the enamel covered that you can wind, make transformers and stuff. But this, it doesn't matter, just whatever you have.
the size is not important, the gauge.
It's less important, yeah. Now, if you're transmitting high power stuff, then yes, it can make a difference. Okay, but think about it. Why are you using a Yagi? Probably it's going to be on your HT, right? I mean, when I put that Yagi on my HT is a 5-watt radio. With the Yagi, it now acts like it's a 50-watt radio, because yes. Yep.
It may act like it in one direction, but it doesn't. It's not omnidirectional.
Right. And that's why I do that. I made that antenna specifically so I can talk to my daughter in Draper. Okay. And she doesn't even need one of those. Okay. Because that also has a better gain for hearing. But I'm making her one as well so that we can point at each other. And that'll make a huge difference.
I used to have a 2-meter Yagi, and I could transmit from Utah State all over Salt Lake.
Yeah. Yep. It's pretty amazing what it'll do. So this hairpin match, it was kind of funny, and you really ought to listen to this presentation. And I was even debating whether or not just to watch the presentation, but I wanted to learn more about it, so I did it. So I had to present it, right? And so it kind of forces you to learn about it. But he was saying, he asked the question, how was I able to figure out what the dimensions of the hairpin is? And he says, well, there's no formula. You just try it and see what the SWR is. And then if it's not to your liking, you make it a little bit bigger and see which direction it goes. Oh, I need to make it smaller, right? And for him, this is for a 2 meter, 3 inches by 2 inches. It worked for the 2 meter. I actually had to change that hairpin because it's a little bit too long. I mean, it works, but that hairpin is actually not ideal. That's why I'm getting ready to put this one on instead. Anywho, he says that the width of the hairpin needs to be just whatever the width of your mast is. Okay, so there you go. And then the length, that's the stuff where you just have to, you start long and then you keep bringing it in until you got a good match. Okay, so here's the question and answer of why a hairpin works. And I am not a RF engineer, so I'm just going to repeat what he said. Okay, because of the additional loading of the reflector and directors, okay, a Yagi needs a little bit of an inductor, which is what the hairpin gives you. Okay, the hairpin actually acts like a coil, an induction coil. And as a matter of fact, you could use an induction coil for that. Okay, but creating coils is, the whole idea is to make it easy. That is not easy to figure that out. So we play around with the hairpin version, right? So start experimenting with the length of the horizontal. Use the antenna analyzer to do this. When you add the reflector and directors to the impedance drops. So what was 72 ohms now, when you added the director and reflector, it drops to 35 ohms, and it develops a little capacitive reactance. Don't ask me what that means. I have an idea of what it is, but I don't know it enough to explain it. So when you add the parasitic elements, the impedance will drop to a complex impedance, 35 ohms, and this is where this is at, 35 ohms resistive, and some amount of ohms negative capacity reactance. That's not a good match for the Yagi. So you add an inductor in there. Okay, so it counteracts that capacitance, and so that's why the inductor is there. Stan, can you better explain what I just said?
Yeah, I can do that. This is the way I always explain it to the student. You don't realize it, but in your home, you're being charged for electricity you're not even using.
I'm going to sue him.
Yeah, and the reason why is because you have a lot of inductive properties with motors and so forth in your home. And it shifts the phase angle. And the phase angle that they're charging you for is the apparent power, not the true power. So if you were to put a capacitor in your home, then you get charged, you know, right amount.
Can I use my wife as a capacitor?
Yeah, yeah. But they have engineers that that's all they do is correct the power factor.
I've heard of that.
Yeah, that's all they do. That's all they do is correct that power factor. So they don't get charged for electricity or power power. A similar thing is happening here. That inductor is going to move it back so there's no capacity reactance. If you have the right amount of inductance, and that would take care of it.
Okay. So
I'm waiting to see the inductor. I haven't seen the inductor. Guess that's coming.
that is the inductor. The hairpin is the inductor.
Is the inductor
Yes.
and the capacitance.
Well, everything else is, when you add the directors and reflector, it
Has capacitive properties.
yes.
Because of the distance between the two isolated elements, you got really good capacitance.
Yeah.
And so you correct them. Okay.
Yep. And there's your little
If you want
choke. Ballon.
to,
Yeah, thank you. Not a transformer, Justin. Just remember that.
It just turns to the pair.
Yeah.
Same,
Coax.
similar on use about 3 turns. Feed line to
Yep.
correct that.
Now, one thing when you're making this, I have on that antenna that's out there, I'm using RG8X, so it's a good quality, but he uses RG58. When it's short like that, having a lossy coax is not as critical. Now, if you're going to run it, anything longer than 15 feet, I would use RG8X for the frequencies that we're using. But that's why I have a BNC on that. I use BNCs at the end of the coax so I can hook it to my HTs, right? Okay, so that is how a hairpin match works. So what's the takeaway? Elements are 0.2 wavelengths apart, plus or minus 5% to create the reflectors and directors. Oh, by the way, putting more reflectors on does you no good.
Oh, really?
Zero. No, directors
Oh,
work. Only one reflector. You have one that's longer.
oh,
Having,
only one reflector.
yeah. Anything more than one reflector, it's exactly. There's zero effect, positive effect for the antenna. The only thing it'll do is make more weight on the back end. And if that's what you're after, go ahead. But as far as the antenna goes, it does nothing for you. Okay, so that's really all that we've already talked about. Now let's talk about the boom. Okay, a lot of different things that we can use for the boom. And here's that feed point J match that I was referring to, how it comes in on itself. That's the same. We could do it that way, which is the J match if you don't want to use a hairpin. But we're going to talk about these elements themselves, and that's going to be really hard to do because these are fiberglass and they're not made out of hangers, right? Metallic hangers. By the way, if you hear a lot where you can make antennas out of hangers, don't use plastic hangers. Okay. Just saying. Okay. And it's really hard to find metal hangers nowadays. When's the last time you've been in a Walmart and saw a pack of metal hangers? I've never seen them anymore. Okay. So you can use booms for just about anything. This is the popular one. This is also the most expensive. This is why I used old TV antennas for the boom to do that. So that didn't cost me anything. Popular one is like making a 1x2. Okay, those are pretty inexpensive and they're easy to drill and very easy to work with. And you put urethane on, and that'll, if you put it up on your house on a tower or something on a mast, it'll be there for years and be just fine. So that's a good way of doing it. Here's Diana Eng. She has a satellite antenna made out of the 1x2, and she has a good time with that.
Now go back to that. Notice that it has,
Horizontal and vertical.
well, not just the horizontal and vertical, but the earplugs,
Yeah.
so that it knows what it's listening to.
No, it's actually, it was actually quite noisy. So you had to use earplugs. Yes.
They're actually to protect you from getting cold, but anyway.
Notice the ones that are out further don't have them on.
One is more likely to focus on that.
Exactly. Yeah. I'm sure that's just for QRM. Who knows? Okay.
Was that a dual band?
That was a dual band, yeah. So 70 centimeter and 2 meter. The Comet one is a very popular one where they use aluminum with the that's like that, but you paid $110 for it versus what she probably spent $10 on everything.
This, is that because when you're talking to the space station, it's on 2 frequencies?
Yeah.
Yeah.
And it's worse than that, actually. Those 2 frequencies change. So you're one person, it's actually a 2-person operation. One person is controlling the frequencies on both the transmit and receive, and the other person is following the ISS. But it's fun to do that. So anyway. Okay, any other wisecracks on this picture? Or can we go? Okay. So let's talk about the elements, and this is what I'm excited to talk about. Some people use the soft copper or aluminum tubing, solid house wire. They work, but this is what you get, right? I mean, it's not the best for longevity, right? It's not durable. So here is what he suggested, and this is this slide here is worth its weight in gold. These are, you can find these anywhere, right? And this is what I've used with aluminum tape. And I purposely didn't do this one just to show you. Actually, I'll do it so everybody can see. So I have the 2-inch aluminum tape. I have the element, and I put a crease. Now, there's two ways of learning. You can learn from someone else's mistakes, or you can do your own mistakes, right? And so learn from my mistake. And that is, I found that if you put a crease on there and then peeled it, it doesn't fall back on itself. And once they stick, you throw it away, right? So I put a crease in there because I don't know if you can see the line down the center, but I drew a line, and that's very easy because all you do is I take my marker, and I'm just going to show you in real time how easy it is. You just make sure it doesn't. And that is pretty near damn perfect. Okay. And I'm just going to finish it. Oh, I only need to finish. Okay, and so the reason why I drew that line is because when I only pull half of it down, and so you got to be very careful doing this because it'll get away from you. But once I pull the backing down, then I'll go ahead and set this, and I'll try to line it up with the line. I tried it without the line, and it's easier if you put a line there, because if you're cockeyed a little bit, then by the time you're wrapping it up, you're thinking, holy moly, I mean, it goes weird. So this, using a fiberglass pull, is wonderful. Now, why does it work? I mean, here's one that I just did this morning, and it's ready to, this is the reflector, and it's ready to use. Why does this work as an antenna element? Because you may be you thinking, well, this is fiberglass. Fiberglass isn't conductive. Why does it work? Anybody have any ideas? Exactly. It works by skin effect, right? Yes. So it doesn't do you any good to even have a solid conductor. What else do you get as a byproduct of using a 1/4 inch, or this is actually 3/16 inch rod, versus a thin wire like this, like a 14 gauge solid wire or a 16 gauge solid wire? What else are you getting when it's thicker, when it's bigger? Maybe. I mean, yes, but there's something that is, yes, Russ.
The center, in essence, is hollow. Right? Because of the skin effect.
Yeah.
And so you're actually getting a larger diameter for nothing.
Okay, but what does a larger diameter do to an antenna? Power? Well, what did you say? Bandwidth. Bandwidth. This antenna that's on the screen, it's probably good for a couple of kilohertz on either side of the band that it was cut for. That GMRS, that is actually was made for 462.65 megahertz, but it'll do every single channel on the GMRS. So I picked I picked the frequency in the center because it works the entire band. Okay. And if you look at the SWR is like this. Okay. If you look at an SWR with this antenna on the screen, it is a dip like that. Okay. It's not broadbanded at all. The thicker the element, the more broadbanded your antenna is. Okay. Yes, sir.
Is that the main factor for the two ends? Is that, or other things in design that affect the bandwidth?
The width.
That's-
That is the thing that makes it.
So you split the tape so it doesn't overlap, it just wraps around.
It just keeps on wrapping around.
So
Yeah.
and multiple wraps.
Yep. To me, you're spending way too much time cutting it the proper width and then forget about doing it exactly, right? I mean, we're not cyborgs. We can't do that. So there's like 3 or 4 wraps on here, which is the reason why these elements are having hard to go in there, because I cut a 3/16 hole, and this goes in just fine, but this is very hard to push through because which is even better because I just made it more broadbanded. Okay. It is more broadbanded than this here, but this is not bad. Okay. Because we're not using wires where there's some depth to it. That is why our TV antennas work so well, because they're hollow and they're wide. Okay. Yes.
Then to dual band later, can you have a broad enough bandwidth to cover?
When we talk about slot antennas, I will show you a single antenna that'll do 2 meter, 1.25 meter, and 70 centimeter. A single antenna because of how broadbanded it is. Okay. But we're talking a nice big wide slot. Okay. The wider the slot on a slot antenna, the more broadbanded it is. The thinner that slot is together, the curve looks like this on your analyzer. Okay. It looks just like how many people have used loop antennas? Loop antennas are notorious for being not very broadbanded, right? And I have a large HF loop antenna, and when I have it on my scope, it is like, it is a very sharp point, right? It's great for that little sharp point, but as soon as I'm off a few kilohertz, forget it. I have to tune it. So, yes.
What about the driven element? When you put that in
Yeah.
whatever, what about the distance between the two elements? Is that critical?
I've done, this is really made for a receive one, and the distance is like a half inch. This is what I have. I mean, you can see what it is right there.
Yeah.
From all the pictures that I've seen, the distance isn't as critical. It just has to be separated. So I don't know if there's a real, I mean, I'm sure there is an answer to that. I just don't know it. But I've seen them where they're closer together than that. I've seen them where they're further apart. Like on this one here, we were talking about antenna mass. I wanted to see what it would be to use 3/4 inch PVC. And I actually, oh yeah, I have something in there, but I have a 4-foot rod in there to make it really, really, really stiff, right? So I can hang this outside and it's not going to bend anywhere, right? So anyway, a lot of different things that you can use for the antenna mast. Okay, so there's that. If you have bicycle flags, that's fiberglass. Anything fiberglassy will work just fine. And the thicker it is, the better. And of course, you just roll it up with the aluminum foil tape, I bought that at Harbor Freight. I think it cost me $4 for that 150-foot roll, or maybe it's a 100-foot roll, but whatever. It's makes all the antennas I want, and that's pretty inexpensive. You know, most of the stuff I've already had.
50 yards by 2 inches or $6.99.
$6.99. How long?
50 yards by 2 inches.
50 yards. Is that what that is?
That's a lot of things.
Yeah, I mean, it's enough to make a few Yagis. So here's one that he did for 2 meters. He has all of the dimensions, but I wouldn't even worry about it. I would put it through the calculator. And so, yes, even you can make your own Yagi. Okay, and that was his last slide on there. Does anybody have any questions on what we talked about?
Finding OTV, and that might be the best way to do it.
Now what the boom is.
Yeah. Yep.
Or the hardest thing now that everybody knows.
I printed up a flyer and gave it to everybody in my neighborhood. And I got about 4 or 5 antennas from it. I says, I will take the antenna off your roof. I think the flyer said, do you still have an eyesore of a TV antenna up there? I wanted them to, I'm trying to sell my services, right? I would be willing to take that off your hands, get rid of that nasty looking antenna on your roof. And so I got a few takes from it, and I took all the elements off, and I have booms now. On these here, this is worth its weight in gold. You can buy the metallic rod, but how many people have priced this stuff at Home Depot or Lowe's? That stuff is expensive. Plus the 1 inch or 1.5 inch square tube. It is very expensive. Yes, you can do it that way if you want to spend it, but this cost. Actually, I got a bunch that were given to the club. So if we want to do this, I can supply as many as I have for everybody.
I can tell you where you get them. You know that Army surplus store on Redwood Road? They've got those antennas, or not antennas.
But they have the bungee in the center.
Well, you can take care of that.
Yeah, I mean, you certainly could, but then here's the point. Anything that is long and thin like this can be used. Okay, whether it's a tent stake or a tent pole or one of these things here. This just cost. I got a bunch of them for free, so that's the best way to do it. And I went to Lowe's, and they had a bunch of different types. One of them was the orange, and they were selling it for like $1.25 a piece, and I bought everything that they had. Okay, because I love making antennas, and so this is what I do. So if we do it as a club, I'm going to bring in the stuff that was given to the club, because I have like 14 of these. So, and by the way, when we're talking 220, I had to use a 4-foot piece per element. Okay. So what do you do? And the reason why I brought the scrap, what do I do with this scrap? Well, don't throw it away. Guess what? It'll make a 70 centimeter or a GMRS Yagi. Okay, so there's 2 antennas. Even though I could only use this for a single element for the 220, and the same thing, it would be a single element for the 2 meter band. The stuff that you can save it, right? Because, I mean, this will do, those just fine.
What did you use to cut them?
I'm sorry?
How did you cut them?
I tried a couple of different ways. The way that I suggest that you don't use, and ask me how I know, is a grinder wheel with, you know, the real thin, with those 3,000 miles, you know, 30,000 RPMs, right? That is not a good way to do this. I was getting splattered with all kinds of stuff doing that. I tried that and no, the fiberglass, it just squishes it.
Really?
Yeah, and I tried that today. And it was a brand new PVC cutter. And so I didn't want to, I mean, you were going down so much and I go, you know what, I'm not going to do it. So I actually used a metal saw blade, a jigsaw. And the fine blade cut it perfectly. Yes, there's a lot of fiberglass dust, so be aware of that, wear protective gear, but it did a nice cut. And that's the hardest thing. When you're cutting the elements, you really got to make sure that you're cutting it. Always cut a little bit longer, because when you put everything together, you may have to shorten things up, okay? It's a hell of a lot easier to shorten it than to pull it to make it longer, okay? Now, and I say that in jest because what could you do? You could just add more tape to the end of it and lengthen it that way, right? So it's not, you know, it's not all lost if you do cut it short, but try to keep it, try to keep them. I found out when I made that one there, it was, I just followed the formula and it was perfect. No. I do all the cuts first and then, so this is the director for the 220 band. So I cut this is 25 1/8 inches. And then I did this here. You could, but I don't know. I didn't want to waste a bunch of tape.
Well, I think you would end up marring your tape more by cutting it on there, because it's more frail than the fiberglass.
Yeah.
So it's,
I can see that happening.
You end up
So
being short.
one thing I also did, just in case, I mean, I'm experimenting with this on the director. I tried on the GMRS one. I tried drilling a hole and putting a screw in there, a number 6, and that worked fine so long as you don't have to unscrew it and screw it in again. I found that which is what I have there now, the hose clamps, the real small 1/4-inch hose clamps, they work perfectly. Okay. And those I ordered online. Those are metallic. I think on Amazon, I search for hose clamps or not. What do you call those clamps that you use for EMT, for electrical? It's the same type of clamps, except they're, I'm sorry? No. They're actually clamps like, as a matter of fact, say? Yeah, a hose strap or a coax strap, whatever. Let's see. Let me. Oh my goodness. Okay, in slideshow. Say again?
Well, pipe strap. what they look like, but they're awfully smaller.
Okay. So let's see. Let me go into Amazon. Amazon. I will show you. Let me sign in and okay. Here we go. This is what I got. I ordered the 1/4 inch. Don't do that. Do 3/16.
So, U-bracket or?
They're conduit clamps.
Yeah. Doesn't affect the overall performance.
Say again?
They may affect the overall performance of the antenna because they're made on.
On the elements other than the director, it doesn't matter. On the driven element, I'll show you what I used right there. So I have it isolated. If you can bring that up and show Stan, you'll see that the driven element has that type of clamp on it. So that's the only thing that you need to be isolated. Everything else can be part of the antenna. As a matter of fact, if you look at the professional antenna, everything is tied to the mast. Yeah, except the driven element. Yeah, that is isolated. Yeah, yep. That's so I can put the coax in there as well as the hairpin. If you look closely on one of those sides, you'll see a hole, and I may have covered it up on both of them, where I used a hole to screw it in. And again, if you're only doing a single connection, that works great, but the hose clamps is a heck of a lot more robust.
Yeah.
So, and I haven't tried adjusting the length or adjusting where that hose clamp goes on the element. Things will change. I may even be able to do it so you don't even need the hairpin by just adjusting it, you know. I mean, it's called experimentation, right? Anywho, anybody have any questions?
Well, I have a comment.
Yes.
Back in the old days when we used to have TV antennas.
Yeah.
You hear about the antennas. They used to, people would get them installed and to the wrong mountains. It should be aimed at the mountains over it, and then towards chemical. But they didn't know.
Well, that's what it looks like an arrow pointed, so that's what we're.
Yeah, that's what they did, exactly.
That's the backside.
And what that will do, it will give you 2 pictures. So you see a reflection. And so when you turn on the
About half a
TV,
second, I would think.
yeah, you'll see a picture, and it looks like 2 heads, you know. That's pretty funny.
So the smaller clamps were, not 3/16, so things like bigger.
No, you said 5/16.
Okay. Let's see, we got a chat here. Pete, I have to leave, okay. Any other questions before or comments?
Yeah, that's good. I'm all up for like an actual activity to build one of these.
Yes, so the obvious next question is, would you like to build a Yagi antenna? If you read my email that I sent out to everybody, that's what I'm suggesting. Justin sounds like he's Okay, so we have some more hands up that would be willing to do that.
What frequency do you want?
Well, that's the question, right? I'm making a bunch of them, so it doesn't matter. But as a club, this one here that I'm just making today, this one was the 223-500, so the simplex. To me, it makes little, especially with the 220 band. Why would you need it when I can, in my basement at 300 milliwatts, hit the Murray repeater, right?
Yeah, it's just,
You know, a thought on that, Bruin is doing a 220 Fox.
He's thinking about doing it.
Well, he's actually doing
Okay.
it. He's ordered them.
Okay.
So, you know, you can, Fox on it, you can,
So what frequency is going to use? Probably going to be a simplex frequency.
I don't know the frequency yet.
I bet you this here will do it. This is cut for 223-500, which is the national, and it is good for 222 to 224. Okay, with the broad bandedness of this,
Which covers all the two.
which covers all the simplex frequencies. Yeah. So if we do the 220 band, we could. I only have 14 of these, right? And so you can either buy 3 yourself, or maybe you buy 1 and the club will supply 2. Depends on how many people want to do it, right? I have no problem giving away all the stuff that was donated to us, right? But I also don't think that it's fair that one person takes 3 of these to do a reflector, driver, and a director. It's not a bad idea to try just a driver and a director, or a reflector and a driver. Okay, that adds, that'll do gain. But having 3 or more elements is the best way to do it when you're doing the fox hunt, right? I'm trying to get Rulin to do a county-wide fox hunt. Because right now, we're just going to go to like a park and do it. I want to hide the fox in Copperton. You know?
allow you to bring the power tools and that stuff in here.
Yes.
Oh, they will.
Yeah. So if everybody is interested in doing that, as a matter of fact, what I'm going to do is I'm going to make a Google sign up form and send it out to the Mark members, not the announcement, the Mark members. And so everybody, are you on the Mark members? Perfect. Look for that, sign up, so we'll know how many to plan for. Okay, and it might be we have enough elements to do everybody. Yes.
It looks like on Amazon, there's 1/4 inch, there's several diameters
Of the clips?
of the markers. There's 1/4 inch and a 5/16. And there's 6 footers as well. They're 90 cents a piece.
Ooh.
1/4 inch ones.
Yeah, that's what these are.
The 1/4.
Quarter, yeah,
Plexiglass, glass.
the fiberglass.
The 4 foot. And that's, so it's $40 for 50 of them. I don't know if they're small. I've heard the farm stores have it's $10 to $20, but that's $2 a piece.
That's what they're actually more expensive at Lowe's and Home Depot with it, unless you can find a good deal.
I've heard of the farm stores.
That's a great idea.
I want to play with.
Yeah.
It looks like if you could figure out the right binding, that you could use the fiberglass as the beam also.
The mast?
the mast. And just figuring out, I've seen people actually 3D printing an adapter.
Oh, yeah, yeah. I mean,
There's some 3D printing examples out there.
as long as the RF doesn't care, right? You can use
For
anything
the
you want.
mast, it doesn't matter if it's conductive or not.
Right. Right. It's a moot point.
There's no advantage to having a conductive mast.
Exactly. Exactly.
Did you
So,
take that one that you built, and tell us what the dimensions are of those?
this,
No, not that one.
this,
Yeah. Oh, that's.
this is, yeah, this is a tape. This is for 2 meter.
What happened to the, oh, you've got it all.
I pulled the elements out, yeah.
What are the lengths of those elements?
I can email everybody. As a matter of fact, what I'm going to do is I'm going to include the Excel spreadsheet that I created. So all you got to do is put in the frequency that you want, and it does everything for you.
Yeah.
Okay?
Well, I think we could do the cutting before we come here.
Yeah.
You know, picking up lines.
Well, what I would do is actually do the cutting outside because it is fiberglass that we'll be cutting. And
You use your electric skill saw.
yeah, I would bring the jigsaw and we could cut them here. That's not going to be a problem, but I'm going to cut them outside.
Yeah.
Okay.
I'm gonna make mine out of green electrics.
Wonder what would that do?
It makes it super powered like a Green Lantern.
Oh, yes. That would be awesome. Okay, so expect a sign-up sheet and we'll go from there. Also, I'm going to put also on the sign-up sheet, what frequency do you suggest, right? And if you give me a frequency, well, I'm going to send everybody the spreadsheet anyway, so you can do whatever you want. So I'm thinking the 223/500 will be a safe one for all simplex frequencies on 220. Okay, that's all I have. Anybody else have anything they want to share?
Multi-band thing is
What about it?
So that's the next lecture.
Yeah, a slot antenna. If people are interested in learning about slot antennas. Fascinating stuff, man.
And when I was at the Grand Junction, convention, the few people had a nice old.
Uh-huh.
When you said your quarter inch diameter rods that you use the 5/16 clamps for it.
Yes. The clamps that I'm using on that are too small, and I've had to bend them out. But even that, it's yeah. And so I'm thinking about actually putting like number 6 nuts and bolts and put it straight through. I think that would tie it a little bit better because right now it's just the metal screw, and that aluminum mass is not the strongest, right? I'm an aluminum, so I think I'm going to. It's a work in progress, but right now it works. But I do want it a little bit more durable. Okay, I was going to show you YouTube. Let's do, come on. There we go. Do-it-yourself slot antenna. We'll learn about making a slot antenna from a Home Depot bucket. There's all kinds of things that we can, obviously we have some guy printed out a rectangle, yeah, a triangle with magnetic feet put on the car. And he was able to really do a great job with that. There is the John. He's the guy who is the antenna master there. John Portune, W6NBC. And so he has a great presentation for that. Okay. If there's nothing else, we'll go ahead and end the recording. Stop recording.